Welcome back, everybody, to part 2 of the inverse function notes. So this was our page from last time where we found the inverse function for a couple of different types of functions. So now we're going to move on to the derivative of those inverse functions. So we've got two theorems here, and they are definitely going to be important to us. First one is telling us that if f is a one-to-one continuous function, then its inverse is also continuous. So that one-to-one property carries over continuity between the two functions, which is nice. And if f is a one-to-one differentiable function for the second theorem, then the inverse function is not going to be exactly the same in terms of its differentiability. We do have to be slightly careful. We have to make sure that this f prime of f inverse of a is not equal to 0. We'll discuss more about that value. But what we do get is that the derivative of the inverse function looks like this for any value of a in the domain of the inverse. So f inverse prime of a is equal to 1 over f prime of f inverse of a. And what this is saying is that the derivative is going to have a reciprocal slope value. So it's going to have a reciprocal slope value. And that's going to be useful for us because as long as we know what that f inverse value is, we don't actually even need to know what the inverse function is, which is going to be very helpful if we don't have an algebraic method for finding the inverse. So before we move to the examples, let's go ahead and jump back to Desmos. So if we look here, we've got the two functions from last time. So this is kind of the most obvious example, a linear function. So f of x is 3x, so it's that taller red graph that is increasing by 3 every unit length. And g is then going to be 1/3 of x. And so we can see here literally the slopes are the reciprocals of each other, and they are inverse functions, of course. Now, a little less obvious is going to be h and k. So that was our cube root and cubic functions from before. So h of x is the cubic function, k of x is the inverse function, which is a cube root function. So luckily we've got Desmos, though, so we can actually compute some slopes here. So if I look at k prime and h prime, they are going to be related to each other. And so in particular, k is my inverse function. So let's suppose I wanted to find k prime of 1. So k prime of 1, I get 0.1666 repeating, which is the familiar fractional value 1/6. So then how would I compute k prime if I didn't know what k was? So what I would do in this case then is try and figure out, okay, well, how does this fit with the inverse value for k of 1? So if I look at k of 1, k of 1 is equal to 4. So from our definitional expression here, it looks like we've got f inverse of a is our input. And so that f inverse of a is going to be k of 1. So going back to Desmos, k of 1 is 4. So then if I put in 4 for h prime, let's see what I get. I get 6, which is the reciprocal value of k prime, what k prime was equal to. So that's the 6 value. So then if I took 1 divided by h prime of 1, h prime of 4, I get the exact same value for k prime of 1 and 1 over h prime of 4. So let's look at that a little bit, further. Let's go to my note here. So this is what I was using from last time. And let's consider how we would normally write y is equal to f of x. And what I'm going to do is I'm going to rewrite that, of course, with inverse notation. So then the question is what is the derivative? What is the derivative of this expression? So if I took the derivative of both sides with respect to x, well, on the left side, we're going to get dy dx times f inverse prime of y, because we have to differentiate implicitly in this case. And then on the right, we're going to get 1. Okay. So then dividing, we get that f inverse prime of y is equal to 1 over y prime, where y prime is, of course, the derivative of f. So we can think of it graphically, and we can choose values. We can kind of work it out algebraically, as we did here. And this is going to be our generalized expression here that we're going to use. That is just going to be much quicker. So we'll spend the next few minutes working through some examples, and then I'll let you do some on your own as well. Okay. So first two examples are just determining if the functions are one-to-one. You can do those two on your own. The same for C. But what I do want to get to is number 2, which will be our first real derivative problem. So we want to find f inverse prime of 1. So let's think about first, what's an f inverse of x? So is there any way I can isolate x in this expression? Doesn't look like I'm going to be able to. Looks like I'm going to be stuck. So there's no algebraic way of finding f inverse in this case. There's no algebraic function that represents the inverse of this expression. So how will I go forward? Well, I know that I'm looking for f inverse prime of 1. So the first thing I should figure out, what's f inverse of 1? Right? So we don't know what f inverse of 1 is, but we know that if f inverse of 1 equals some numerical value, let's say k, then that's the same as saying f of k is equal to 1. So if I take my function expression then, and I make these k's, so k plus cosine of k equals 1, can I solve for k? Well, turns out I can, at least in a very simple value. So take a moment and think about what value would give you 1 here. And if you guessed correctly, you would get k is equal to 0. So 0 plus cosine of 0 is 1. So that is going to be the value that gives us 1 in this case, which means that f inverse of 1 is equal to 0. Okay. So that's going to be useful, since I know that this is equal to 1 over f prime of f inverse of 1. Which is going to be 1 over f prime of 0. So the question now is, what's f prime of 0? So f prime of x is equal to 1 minus sine x. So then f prime of 0 is going to equal 1 minus 0, which is 1. So the derivative of my inverse function at 1 is 1. All right, so for number 3, go ahead and pause the video, give it a try on your own, and then we'll come back together and solve it together. Okay, so for this one, we're going to do the same sort of trick. So we know that f inverse at 2 is what we're looking for, or G inverse at 2. So G inverse of 2 is K, let's say, which means that G of 2, G of K is equal to 2. Okay, so then if I set my expression equal to 2, take a moment, think about what x value would give you 2 in this scenario. And if you guessed x equals 1, you would be correct. So x equals 1 is going to be our value of k. So that's going to be our equivalent k value. So then over here, when I'm finding G inverse, I know that that is equal to 1 over G prime, G inverse 2, which is going to equal 1 over G prime of 1. So G prime is going to be 1/2. Oops. I think I'm running out of space here. Let me get rid of that. And let's move this over here. So G of x was equal to the square root of x cubed plus x squared plus x plus 1. So G prime of x is going to equal 1/2 x cubed plus x squared plus x plus 1 to the negative 1/2 times the derivative of x cubed plus x squared plus x plus 1, which will be 3x squared plus 2x plus 1. So we're going to multiply all that together. So G prime of 1, which is our value, is going to equal 1/2. This expression is simply going to be 1 over the square root of 4. So that's going to also be 1/2. And then this guy at 1 is going to be 3 plus 2 plus 1, which is 6. So it looks like we've got 6 over 4 or 3 over 2. So 1 over 3 over 2, which means 2/3 is our derivative. And again, I don't actually need to find the inverse function because we're only interested in that particular value. Okay, so below that, we've got a table example. So we've got a table of values for x, f, and f prime. And we're being asked to find 2 particular derivative values. So I will go ahead and let you find that on your own, and you can check the notes online. So this is going to conclude our notes for inverse functions.